Good morning, everyone. Today I'll just discuss about the lattice. Lattice. So we have already discussed about the lattice, and lattice is something that relation with the conjunction, disconjunction relation in between two elements. I've already discussed what is the lattice and what is the form of the lattice. The lattice means that is both relation with the conjunction and disjunction. And we have just represented like this format. A conjunction B and B conjunction A. A conjunction B. That means infimum of AB. B conjunction A disjunction B. That means maximum of AB. Or this is also called as the supremum of AB. So this is the lattice, we can say. So we also should consider the another definitions of the lattice. What is the another definition of lattice? Some theorem and some statements we have to just explain here. First point, just remember. Let lattice less than equal to criteria be a lattice. L less than equal to be a lattice. In which supremum and infimum relations or disjunction and conjunction relations or meet or join relation denote the operations. This relation is generally called as the disjunction and this is called as the conjunction. Conjunction relation just represent here meet. This is meet we can represent. And another one we can represent it join. Suppose so that AB belongs to L. A, B, two elements, and which belongs to L is there. And just we can satisfy these above conditions, L less than equal to B. First criteria. That double implication, A conjunction B is equal to A. A less than equal to B. A disjunction B is equal to B. That is the also that is condition for the lattice. A less than equal to B and A conjunction B is equal to A. That is the criteria. A less than equal to B, a disjunction B is equal to B. That is also. So another condition, let L less than equal to, what is the lattice? Second point, let L less than equal to be a lattice. Right? And AB belongs to L, we can say, just we can consider two elements, and that is A comma B, and which belongs to L. And which satisfy the following condition, then we can say that is a lattice. If satisfied the following condition. Satisfied the following condition. What are the following conditions? Now, first condition, A less than equal to B and L less than equal to C. L less than equal to B and L less than equal to C. then you can say that A less than equal to B disjunction C. A less than equal to B disjunction C. That is the first law. And second condition, A less than equal to B and A less than equal to C, and it also satisfied A less than equal to B conjunction C. These are the two properties, and this property is also called as the dual theorems, or this is called also duality theorem. This relation called as the dual theorem or duality theorem. This is both conditions satisfied, that may be a lattice or that is a lattice, and if this condition is satisfied, any two number which belongs to lattice, and that is called also dual sets or duals of the theorem. Duals of the theorem. Or duality theorem, we can say that one. So how to prove it actually duals theorem? We can prove again. First of all, we go what are the, that is second condition, and third condition we can aim here for the case of third condition. For ABC belongs to L. A, B, C belongs to L lattice. Then L less than equal to L said to be a lattice. L less than equal to, we can say that is a lattice. If some property is satisfied. What are the properties? If L less than equal to B, L less than equal to B, implication A disjunction C less than equal to B disjunction C. A less than equal to B, and which also satisfied A conjunction C less than equal to B conjunction C. This both the condition, if it is satisfied, then this is also A, B, C also called as the lattice. There is also one property you have to remember this way. For any number, another property is also for a lattice. L less than equal to B a lattice. Let L less than equal to B a lattice. For any ABC belongs to L, belongs to L. If this is also ABC belongs to L, or this is also one property satisfied. If it is satisfied, that is also called as the lattice. Another property was also there. L less than equal to B, L less than equal to B implies A disjunction C less than equal to B disjunction C. Already have told this also. B disjunction C. And this is also same property, A conjunction C and B disjunction, this is also called as the lattice. We have already explained this, yes. Another one property, and also that is called the distributive lattice. If satisfied the following condition, let L less than equal to be a lattice. Then what happens? L less than equal to For any ABC belongs to L, suppose three elements we consider, that is A, B, C belongs to L. And following properties should be: A conjunction B disjunction C, that is greater than equal to A conjunction B disjunction A conjunction C. And another property is also there: A disjunction B conjunction C less than equal to A disjunction B conjunction A disjunction C. If this property is hold, that is also we can say that is a lattice. Also we can say that the modular lattice. What do you mean modular inequalities? We will discuss about the modular inequalities or modular lattice. Statement of modular lattice. Modular lattice. What is modular lattice? We define, let L less than equal to be a lattice for any ABC belongs to L. A, B, C belongs to L. And following considered properties should be hold here. Then we can say that is the modular lattice. A less than equal to C, double implication, A disjunction B conjunction C, that is less than equal to A disjunction B conjunction C. This is called as the modular lattice. How to prove it? Actually, this is a modular lattice. So just we come to prove this modular lattice. So first of all, we consider three elements. We consider that is in the lattice. A, B, C belongs to L. These three elements we consider for this lattice. And just we consider one A is less than equal to L. Double implication is there, so E less than equal to B. That means we can see that A less than equal to A less than equal to C is there. That means A disjunction C is equal to C. That is a property. If A less than equal to C, then this property must be hold. Again, from this criteria, just we found. Now let A disjunction B conjunction C. A disjunction B conjunction C. What is the value? That is less than equal to A disjunction B and A disjunction B conjunction A disjunction C. We already defined here A disjunction C is equal to C. So A disjunction B conjunction C. So this is already proved, and this is the modular theorem. Modular lattice. This is called modular lattice. So first of all, we define this value and we prove the modular lattice and dual of the lattice. What is the criteria of the dual of the lattice? We have previously defined here the dual of the lattice also. What is statement of dual of the lattice? The dual of the lattice means two conditions must be satisfied where A, B, C belongs to L. Just you can define A, B, C belongs to L. And dual of the lattice satisfy this condition A less than equal to B and A less than equal to C implies A less than equal to B conjunction C. Second condition, A less than equal to B and A less than equal to C implies A less than equal to B conjunction C. If दोनों conditions satisfy होगा, but these both the conditions are satisfied, then this is called the dual of the lattice. First of all, we can say B conjunction C, or we consider B conjunction C means supremum value of B and C and infimum value of B and C. Both the conditions are required here. So we just consider let B conjunction C, B disjunction C, that means supremum of BC, B comma C. So A less than equal to B, A less than equal to B, and A less than equal to A less than equal to B, B less than equal to supremum of B comma C. Or that is also we define here A less than equal to B we define and B is less than equal to B disjunction C. Right? Just we can compare both this value. A less than equal to B and B less than equal to this value. Then finally we can subvert the transitive criteria. We can say A less than equal to B disjunction C. Less than equal to B disjunction C, and by this is satisfied by the transitive criteria. Transitive rules are defined here. Again, another property we also need to show that the disjunction conjunction value also is there. A less than equal to B, first criteria. A less than equal to B and A less than equal to C. Then you can compare here A less than equal to B and A less than equal to C. Then A must be less than equal to. Then we can say that A must be less than equal to B and C. That is B conjunction C. A less than equal to B conjunction C. And this is the case of second case. We can prove it. And this is called the modular lattice, or this lattice we can prove. Sorry, dual of the lattice. Not this is the dual of the lattice. Another case also we have to discuss about here, isomorphic lattice. And isomorphic lattice we need to show it. So what is isomorphic? Let L1 isomorphic lattice. So we can say isomorphic means Let L1 and L2 two lattice. L1, L2, both are lattice. We say that lattice L1 and is isomorphic to lattice L2. Lattice L1 is isomorphic to lattice L2. If there exists one-to-one mapping, if there exists one-to-one mapping, 1-to-1 mapping, from L1 to L2, from L1 to L2, then we can say that that is isomorphic condition, and such that if A conjunction B, that is equal to FA conjunction FB. Another property, F A disjunction B is equal to FA disjunction FB. These two criteria must be satisfied. Just to remember, when in the above definition we call isomorphism, L1 is equal to L2, then F is called automorphism. If L1 and L2 both are equal, if L1 is equal to L2, L1 and L2 lattices, if both the lattices are equal, then F is called then function, because function F is mapping from L1 to L2. That is defined for the homomorphism. And if L1 and L2 both are equal, then it is called automorphism. L1 L2 is equal, then it is called automorphism. Right? L1 and L2 both are equal, then you can say that that is the automorphism. Okay. So that is, we have to define the relation for the automorphism, homomorphism, and lattice, the different cases we have to discuss here. And just we'll discuss some bounded lattice. Bounded lattice already have discussed the greatest value, greatest element is 1 and least element is 0. That lattice is called as the bounded lattice. Greatest element 1 and least element 0, that is called bounded lattice. Greatest element 1 and least element 0, then this lattice is basically called as the bounded of lattice. And some property also I have discussed here. So this is called as the bounded lattice. Again, some lattice is called 0 is the identity operations of conjunction, and 1 is the identity operation of 0 is the identity operation of disjunction, and 1 is the identity operation of conjunction in a bounded lattice. So let L is called the complete lattice if every non-empty lattice L has supreme and infimum in L. So complete lattice meaning क्या होता है? What is the complete lattice? Every lattice must be contains supremum value and infimum value in L. That is called complete lattice. Every lattice contain supremum and infimum in L. L. Then this lattice is called as the complete lattice. Okay, so thank you. We'll discuss again in the next class.